This lecture is for ELEC 1510 Logic Design. This is Lecture 20, Video 1 on Analysis of Sequential Circuits, corresponding to Textbook Section 5.5. The analysis of sequential circuits is essentially the backwards version of the design of sequential circuits. So we're going to start off with a circuit diagram and eventually work our way back to the state diagram to figure out what this circuit is actually doing and what purpose it could serve. In the circuit diagram that we see here, we have a single D flip-flop, two inputs X and Y, and an output A that corresponds to the output from the flip-flop. So that output is both our state and the actual output from the circuit. X and Y go into an XOR gate, and A goes into a second XOR gate with the output from the first XOR gate, forming the input to the single D flip-flop. I should mention that this example is taken from the textbook as well. What we want to do is actually determine the logical equation for D to figure out what the next state is as a function of the inputs in the current state A. So D, as an unsimplified logical function, is A exclusive or, parentheses, X exclusive or Y, which we can rewrite as being A exclusive or, parentheses, X prime Y or XY prime, which then becomes A prime parentheses X prime Y or XY prime, or A parentheses X prime Y or XY prime parentheses prime. We distribute the A prime into the first parentheses to get A prime X prime Y or A prime XY prime, or then using De Morgan's theorem, A parentheses X prime Y parentheses prime parentheses XY prime parentheses prime. So those first two terms stay the same. The second two terms, I again apply De Morgan's theorem to get A parentheses X or Y prime parentheses X prime or Y. Distribute those. Again, the first two terms stay the same, so the second collection of terms becomes A parentheses XY or X prime Y prime. And then finally, we get A prime X prime Y or A prime XY or AXY or AX prime Y prime. So that would be min terms 1, 2, 7, and 4 for D. So that means that whenever those variables take any of those min terms, those variables being A, X, and Y, D, or the next state, will be a 1. So now, using the equation that we derived for D, we can assign the next states by saying that the next state of A is going to be equal to D. And using those four min terms, we can assign 1s to those values. That was A prime X prime Y, A prime X Y prime, A X prime Y prime, and A X Y. So we know that for the state table, given the current states and the two inputs, we can determine what the next states are going to be. Doing all this allows us to then work backwards and draw a state diagram for that circuit. We have two states that are just labeled 0 and 1. We could potentially just relabel those A and B if we wanted to. But in either case, if you have at the input 0, 0 or 1, 1, you return to the same state. And if you have the two inputs being opposite, 0, 1 or 1, 0, you move to the other state. So that's what that circuit was doing that we saw a few slides ago. So here we see a more complicated state machine circuit. This one uses JK flip-flops, and there are two of them. There's a single input X, and then there are two outputs, which are just the state variables A and B. So the first step, again, is to derive logic functions for the inputs, and we'll call those J sub A and K sub A for the JK inputs to the flip-flop that has output state variable A, and then J sub B and K sub B for the JK inputs to the flip-flop that has output B as its state variable. J sub A, as you can see, is just B. K sub A is going to be X prime B. J sub B is X prime, and then K sub B is X exclusive or A, which we'll just rewrite as being X prime A or XA prime. Now we write out the state table, and we have to add some additional columns in the state table for the flip-flops because the flip-flops are not equal to the next state like they are for a D flip-flop. So we need to determine the transition between the current state and the next state binary values based on how the JK inputs are assigned. Okay, so we have all of the possible values for the current states and the inputs. Again, we have two current state variables, A and B, and one input X. All right, so based on the equation for J sub A, which was B, we can just fill in the column for J sub A as being equal to B. The equation for K sub A was X prime B, so K sub A will be a 1 whenever X is a 0 and B is a 1. That only happens in two places, so it's 0, 0, 1, 0, 0, 0, 1, 0. J sub B is X prime, so we just fill in that column as being the opposite of X. K sub B is X prime A or XA prime, so we can fill in that column as well. All right, so now we need to look at the JK inputs for both flip-flops, and using the transition table for JK flip-flops, which is where if J and K are both 0, the transition from the current state to the next state is no change. If J and K are 0 and 1, the transition is that it just becomes a 0 in the next state. If J and K are 1 and 0, the next state is a 1. And if J and K are both 1, the transition is a toggle. So that's either 0 to 1 or 1 to 0. All right, so we can look at the column for the current state of A, look at J sub A and K sub A, and then assign the next state column for A based on that. So you can work through that if you want. Then we look at the current state column for B, look at J sub B and K sub B to assign either no change, 0, 1, or toggle, and this is what we get for B. Again, you can work through that if you want. This will allow us now to draw out the state diagram because we have the current states, the inputs, and the next states, which is all we need to draw out the state diagram. And the state diagram for this state machine looks like this. We have 4 states. Again, I haven't labeled what the states are. I've just left them as their state variable binary numbers and the transitions in between them. There are no outputs labeled because the circuit had no formal outputs other than just the state variables. And it's a little hard to tell what the purpose of this circuit is. It doesn't seem to necessarily do anything that we can tell right away like the last one did. But this is what the transitions are going to be for this state machine.